for designing the rotor and stator blades in the 3D inverse design software Turbo Design 1, when we launch the software, this is what we see. This is the GUI, and then we can start by opening the files that were exported from the mainline code Turbo Design 3, and we can see two files were exported, one for the rotor and one for the stator, and we can select the rotor file first. And we can see all these sections have now been pre-filled from that information from that mainline code. And so if we start with specifications, we can see the rotational speed, volume flow rate, number of blades have all been pre-filled. And then the next section is meridional design. And if we open the plot first, we can see the meridional shape for the rotor is here, just like we saw it in the TD3 report. And at the same time, we can also see there is a 2D grid for the blade design. And the thing about inverse design is that although this is a 2D grid, there is the third dimension is solved using Fourier transforms. And so even though this is a 2D grid, it's even though it's a 3D solution, it's still very fast. The next section is thickness, and this is where we specify the thickness of the rotor blade, and we have different options to do that. For example, normal or tangential, and also we can specify different distributions. For example, constant from leading edge to trailing edge, or NACA profile, which we have selected in this case, and then we can very easily plug in the NACA code just like that. Now the next section is blockage, and this is something we use only for very high speed machines, transonic machines with significant boundary layer blockage. But since this is a subsonic compressor, we can skip this section for now. Now this blade loading is the most important section when it comes to inverse design. And so if we start with looking at some plots first, and these two plots are the blade loading plots basically. And on the left, this is the span-wise loading. So this is the leading edge, this is the trailing edge, and 0 is hub and 1 is shroud. And we can see that the leading edge has a 0 swirl because of the axial flow coming into the rotor, whereas there is a finite value at the trailing edge. And in this case, we have specified a pre-vortex distribution, so the work coefficient stays constant from hub to shroud. And once we have set the span-wise distribution, the next thing is the stream-wise blade loading from the leading edge to the trailing edge. And in this case, we can see that the default loading, which came from the mainline code, is a mid-loaded sort of distribution. And so once we have set the span-wise and the stream-wise loading distributions, then the next section is the stacking. And stacking is what defines the lean of the blade or the wrap of the blade on any one direction. And so for now, we can go with a 0 stacking, and this means basically a straight or a radial blade. So once we have completed all the inputs, and then we can actually click on run to get our first rotor blade design. And we can see in just less than 5 seconds or so, we have our first rotor design, and this has appeared in the project manager window as well. And so we can start by looking at some plots first. So we can create a 3D plot, and this is how the rotor blade looks, the initial design. And we can also have a look at all of the blades together, and then activate the hub as well. So this is the 3D view of the rotor row. And at the same time, we can also create some 2D plots. So for example, let's go for the Mach number distribution on the blade surface, and we can actually have a look at different span-wise locations. So this is showing you the distribution at the hub, midspan, and the shroud. And we can see the distribution is pretty smooth for all throughout the blade surface. And in the 3D plot, actually, we can also have a look at some 3D plots on the blade surface. Let's go for Mach number again. And so here we can have an idea of the Mach number on the blade surface. And then we can actually make some modifications to this initial design. So for example, if we saw that the choke flow is not sufficient, or the choke flow is actually less than the design flow rate, then we can simply increase that choke flow by increasing the throat area of the rotor blade. And that we can do by simply increasing the leading edge loading in this area. So we can do it by simply dragging these points up, and then we can just click run again to get the new design. And again, very quickly, we have our new design right here, and also we can see how the Mach number distribution has changed because of that opening up of the throat. So we can actually have a comparison of the plots with the previous design, and we can clearly see the throat has opened up the plots at the leading edge. And another modification that we could do is, for example, if we see that the rotor is not able to achieve the desired pressure ratio, then we can easily go into the blade loading again, and this time we can have a look at the span-wise loading. And let's say we wanted to increase it by 10%, so 0.4 to 0.44 or something. So we can easily do it like that, and then click run again. And as simple as that, we have the new design again. And this one has a higher work coefficient than the previous design. And we can also do a comparison with the previous design. And we can see how the loading has actually increased for all the three sections because of that increase in the work coefficient that we specified. And so once our rotor is ready, we can actually change the name to rotor in the project manager window. And once the rotor is ready, we can actually go into designing the stator. And for this, we can again open the file. Sorry, if we want to retain the cases, then we need to click on import, and then we can select the stator file that was exported from TD3. And now what we will see is all of these different sections have been updated with the stator settings. So that's the meridional view for the stator, and the thickness again is a NACA profile for the stator. And if we come to the blade loading now, what we can see is the leading edge loading is actually very close to what we had for the stator trailing edge, and this actually ensures a good matching between the rotor and the stator automatically. And at the trailing edge, although we want a zero swirl coming out of the stator, the mainline code actually gives a slightly negative loading at the trailing edge, and this is to compensate for the viscous deviation. And for the stator as well, we can see that the default loading that came out of the mainline code is a mid-loaded distribution. And so once again, we have the settings ready for the stator, and we can click on run again. And again, very quickly, we have our stator blade ready, and so we can have a look at the some plots. So that's the 3D view of the stator blade, and then to see the complete blade row, you can also turn on the hub. So that's how the stator is looking like. And we can actually also create 2D plots, just like for the stator, and then this time perhaps we could look at the static pressure distribution at all the 3 sections. And again, we can see the distribution is pretty smooth throughout the blade surface. And for the 3D view as well, we can have a look at the static pressure on the blade surface. And so in the project manager window, we can see we have our stator case has appeared here, and we can rename it to stator. And now in the 3D view, actually we can see both of the blades together. So if we select the rotor as well and go to 3D view and geometry and then combine the 2 plots, then we can see how the arrangement looks like for the rotor and the stator rows together. So this is the view of the complete stage. And next, if we bring our focus to the project manager window, then we can see there are some performance parameters available here, and also some geometry parameters. And these have some very useful information of the performance of the different components that we have designed. And for example, in the case of axial compressors, profile loss is very important, and diffusion ratio, because it gives an idea of flow separation possibilities. And also leakage can be important for the rotor especially, and the throat area of course is very important as well, because this determines the choke flow. And once we have selected the parameters of interest, we can go for seeing only the selected ones. So we can see now, if we look at the rotor and the stator, we can see the difference in the different parameters between the 2. Of course, stator won't have any leakage loss parameter, because usually there is no tip clearance for stator. And we can clearly see that the stator throat is much higher than the rotor throat. And this means that the rotor is the one that's going to set the throat for the stage as a whole. And again, we also have some more options. For example, a 2D plot to look at these parameters in perspective. So for example, if we select the profile loss, then we can clearly see that the rotor profile loss is actually much higher than the stator profile loss, and kind of obvious because this is a very high reaction stage, about 80%, so most of the pressure rise comes from the rotor. And similarly, we can select any other parameters of interest, for example the diffusion ratio, etc. And once we have the 3D blade designs ready for the rotor and the stator, we can go about exporting them. So in the export section, we can actually select the type of leading or trailing edges that we want. So we have the different options like tangential graph or elliptical. So we can select them here. And then for the domain, we can actually select the type of domain. So for example, if we wanted to go with the CFD run, so we can select the CFD single passage in this case. And finally, in the output, also we have different formats that we can choose from. For example, IGS and step files, or we can even choose to select turbo grade curves. And so and then we can browse to the directory where we want to export our curves, and then using this button we can export the blade profile curves. And in this way then we can proceed to a CFD analysis for the rotor and the stator.